The John H. Martin Award recognizes a paper that has led to fundamental shifts in research, focus, and interpretation of a large body of previous observations. The 2022 John H. Martin Award is for the influence of oxygen exposure time on organic carbon preservation in continental margin sediments by Hartnett et al. For describing oxygen exposure time as both a concept and a quantitative parameter, which have revolutionized the study of organic matter preservation in marine and lake sediments. Hartnett et al., which was published in 1998 in Nature, was foundational to the fields of oceanography, microbial ecology, organic geochemistry, and geology by developing a novel parameter, oxygen exposure time, that provides an integrated measure of the different processes influencing carbon preservation. The tool to predict carbon burial efficiency described in this paper was elegant and revolutionary to the field. More than 20 years later, this concept continues to be integral to oceanography and limnology, particularly as we continue to assess how climate change impacts on aquatic ecosystem oxygen dynamics will influence carbon sediment burial. Please join me in welcoming Dr. Hilary Hartnett.
Thank you, Amina, for that really lovely introduction. Yes. And thank you, everybody, for being here today. So I'm really, entirely pleased and, to be honest, gobsmacked to be receiving this award on behalf of my co-authors. And I didn't know John Martin, but in my first year in graduate school, 3 separate classes had us read his iron hypothesis paper. So it was somewhat clear that this was revolutionary. And the idea that our paper is now within that canon is a little overwhelming. I saw John Martin give a talk in 1992 and was unaware at that time that he was a polio survivor and used crutches and a wheelchair later in his life and maintained a field career. And I think we all need to pause and remember that our sciences are not always that accessible. And in that realm, I would like to dedicate this talk to Marilyn Fogle. Marilyn Fogle was a kind and wise and brilliant scientist who also had a long fight with ALS, which she lost last Wednesday. But she became a tremendous advocate for accessibility in our science, and I want to dedicate this talk to her. So, I am accepting this award on behalf of a team, though I'm the only one who can be here today. That team includes Keil. This is a relatively recent-ish picture of Rick. John Hedges, who we also lost in 2002, and Al Devol, who was my advisor, and I like using the picture of Al from 1996, though he would probably appreciate the more recent photograph. Al is best known as a denitrification guy, but he's also an expert sediment geochemist, and everything I know about sampling sediments I learned from Al. He retired, 4 or 5 years ago, and is still going out on student cruises as a bastion of knowledge, at least up until COVID time. So these are my earliest mentors and my all-around champions. And that leads me to my first piece of miscellaneous advice, and this is directed mostly to the early career scientists in the room. Find a mentor. And I'm not being glib. If someone doesn't present themselves, ask them if they would be a mentor. We need mentors all the time. Even at my stage in career, and I didn't know I needed mentors, Marilyn made it clear to me that I needed a mentor. So this paper was almost entirely analog, right? It was published in 1998. We communicated with our editor via fax machine. We submitted papers in 5 or 10 copies of hard copy in these fat boxes. And I even found one of these. For those of you who don't know what this little thing is, this is a 35mm slide, which is how we used to give talks, and you had to have them in order in little cartridges, and they often fell on the floor and chaos would ensue. But one of those faxes gave us some signs that we were onto something. This is a fax from John Hedges. He was very excited about the draft. And he says, "My guess is that you've written a classic." This is March of 1995. "It will certainly be one of the most important papers on the topic of sedimentary organic preservation, and honestly, I did not know I still had this fax." It turns out, he goes on to say there are some places where you might consider some subtle changes, and the fax was 2 pages long. The other thing is that we were at the cusp of email, because shortly after the fax arrived, I got this email, which was printed out and stapled to the fax that says, "Dear Hilary, I just sent you a fax." Here's some little known facts about this paper. This is the first paper I ever wrote. Absolutely the first one. It was work for my master's degree. The other little known fact for this paper that has been acknowledged as important, it had 25 data points. That's it. I know and love every single one of them, and I'll show you in a couple of minutes just how hard each one of them was to get. And sort of thinking about this paper, I also realized this paper did not go smoothly through the review process. We submitted it in the spring of '96. It went through 2 rounds of what I can only call contentious review. The reviewers all agreed that the data was great and disagreed strongly as to whether or not this result was novel. So the editor sent it to an arbiter. And the arbiter asked for a 3rd round of review and then a 4th round of revisions, and it was finally accepted, which at this stage I was not expecting. And then Nature sat on it because they actually put it into the issue that came out in the same week as Ocean Sciences. And that generated a tremendous amount of buzz. So miscellaneous advice number 2 and 3. 1, sometimes saving random things pays off years later. And 2, actually I guess 3, trust the review process. It's not always easy, but if you can maintain a little bit of clarity that is not personal, it will make your paper better for it. So, the real question is what controls organic matter preservation in sediments? That has been a question at that stage for 30 to 40 years. And the reason it's a big question has to do with this. This is the schematic of the global carbon cycle, and burial in sediments, way down here, is the connection between this surface fast cycling primary production carbon cycle and the long-term deep slow carbon cycle that connects to sedimentary rocks. This tiny little leak of carbon into the seafloor controls how much organic matter gets into the sedimentary rock and kerogen pool, but it also is a profound feedback on oxygen in the atmosphere. And the reason that works can be boiled all the way down to this. This is that classic cartoon photosynthesis equation where CO2 and water make organic stuff. Note I put it in quotes because there's no molecule that looks like that. And when you run this forward, it's photosynthesis. And if you respire that organic carbon with oxygen the other direction, you make the same number of moles of carbon as you do of oxygen. And if they were perfectly balanced, everything would be fine, but there'd also be no oxygen in the atmosphere. The negative feedback comes in because when you bury a little bit of that carbon in the seafloor, that oxygen is free to be in the atmosphere and dissolved in the ocean. And so the more carbon you bury, the more oxygen you produce. But that oxygen is the best oxygen around, and so more oxygen also leads to more organic carbon degradation, thus the negative feedback. And we can see that there's a clear correspondence between regions of the ocean that have high organic carbon in sediments and low oxygen. So this is a map of surface carbon content. Red colors are more carbon, and you can see it's high along upwelling margins in the eastern tropical Pacific, here in the Arabian Sea. And this is oxygen concentration in the water column, about 300 meters. And you can see that low oxygen, sorry, the color scale is opposite now. The reds are really low oxygen concentrations. Eastern tropical Pacific, upwelling margins, and Arabian Sea. So up until this point, the problem is that the focus was either on input controls, primary production, rain of carbon out of the surface zone, bulk sedimentation, or on the removal zone, oxygen concentration, maybe flux, carbon oxidation. And it was very, very clear that the heart of the controversy is that no single factor would be a definitive control on carbon preservation under all conditions. So a useful parameter needed to address both input and removal. It should work in a wide range of environments, low and high oxygen, and ideally it should count for this long-term negative feedback between organic carbon and oxygen. So our paper set up both an independent measure of burial, that's the burial efficiency, and an integrative controlling factor. That's the oxygen exposure time. Now, we didn't invent burial efficiency. It's the percentage of carbon buried in the sediments as a fraction of the total amount of carbon that got there. We did develop this way to measure oxygen exposure time. And so what we really have is a budgeting approach. It's a lot of work to constrain a carbon budget in the sediments. We did this over 5 cruises, 2 to the Mexican margin where there's low oxygen, 3 to the Washington margin where there's lots of oxygen. And we measured each of these pieces. We measured input, either with sediment traps or we calculated it. We measured carbon oxidation using benthic flux chambers or landers or pore water profiles. We measured carbon burial. You have to both measure carbon content and a sediment accumulation rate. That way you can calculate the fraction of the input that burial represents. And we measured oxygen exposure time by measuring the depth of penetration of oxygen in the pore water, that's the dissolved gas in the pore fluid, and sedimentation rate, so we could calculate the length of time a sediment was exposed to oxygen, that's the depth of penetration divided by a sedimentation rate in length per time, so you end up with units of years. These you all measure at sea. These you all measure in the lab. It was kind of a lot of work. For those of you who haven't done benthic flux measurements at sea, I think it's always worth showing a little bit of a picture. This is Al's lander. It's a little fuzzy because it's a real live 1980s, 90s photograph. It's basically a fancy bell jar. You set it down on the sediments and you isolate a patch of sediment and overlying water. And these syringes, powered by little springs, collect a water sample from the overlying water every few hours, and you can make a plot of oxygen concentration versus time. That's a direct measure of the consumption of oxygen in those sediments. And if you don't have a lander, you can take pore water profiles. So here's concentration of oxygen across the top, depth in a classic oceanography positive downward plot, and oxygen concentration decreases steadily. And in both cases, you can then calculate or model the change in oxygen concentration and the depth of oxygen penetration. So where do we get? This is the main figure from the paper. Carbon burial efficiency, which says what fraction of the carbon that arrives at the sediment survives to be buried, as a function of oxygen exposure time in years, and it's a log scale, so these are really short. These are thousands of years. And despite real field data that has all these parameters built into it, right, sedimentation rate, and penetration depth, and benthic fluxes, there's a really, really lovely correspondence between high burial efficiency here in oxygen deficient margins where the exposure times are really short, moderate exposure times and moderate burial efficiencies in these kind of shallow to mid-depth margin sediments. And out here, where you have deep margin and open ocean sediments, you have long exposure times and very low burial efficiency. And this basic relationship is held up across a wide range of environments by many other investigators for many, many years. So what does it mean for a paper to have influence? Well, it could mean citations, sure, it's got them. Or maybe you realize that the paper occupies some kind of central hub in a network. This is from Connected Papers that lets you see whose papers have cited you and where you fit into the community. But I think it's more about how the community uses the paper. This is the data from Scopus of all the papers that cited it. And about half of them are in the earth and planetary sciences. But there's a significant fraction from the agricultural literature. There's environmental science and interdisciplinary things starting to show up in the energy and physics community. I really like this other, which includes the social sciences, microbiology, math, and computer science. This paper has had far more reach than we ever really intended. And of course, I did a requisite word cloud based on the titles of the papers, and you see the things you expect to see, right? You see carbon, you see oxygen, you see organic matter, marine sediments, but if you dig deeper, there's lakes, there's coastal stuff, there's biomarkers, there's nitrogen and phosphorus in here, there's lipids, there's climate, there's a bunch of regional things. It was really kind of cool to see all this. So in just the last year, I kind of wanted to know what was happening with this paper. And this highlights just a few. Here's a paper on oxygen minimum zones in the Indian Ocean, soil carbon loss as it relates to fire, link between chlorines, which are a chlorophyll degradation product, and chlorophyll production in the oceans. This one's about the whiff of oxygen 2.5 billion years ago at the Great Oxidation Event. Hydrocarbon generation and petroleum potential is still a subject that this paper gets connected with. And this one's about evaluating the risk of harbor contamination and coastal conservation. And these are just the tip of the iceberg. It's kind of amazing that the community uses this work in so many different ways. And it still informs my own research. I was on a cruise in 2018 in the Indian Ocean. There's my whole core squeezer, just like the one I used in graduate school, working on estimating burial efficiency and exposure time for these deep Indian Ocean sediments. I've also been doing work with a Frontiers in Ecosystem Dynamics, Earth Systems Dynamics team on the Great Oxidation Event in the Archean. And it turns out the sort of oxygen flux balance approach to thinking about why we developed oxygen 2.5 billion years ago is tightly tied to understanding organic carbon dynamics. That's hard, so we don't have a good indicator. And I also do work now in what you can only call astrobiology. And it turns out my approach to low oxygen systems is relevant because there's only one system in our solar system that has oxygen. All the other planets we think about, we know to be basically anoxic. And my planetary science colleagues ask me all the time, what are the oceans going to be like on other planets? And it's like, well, we know basically nothing, so let me tell you what I think. And we write papers about oxygen in planets with oceans around other stars, which we haven't found yet. So where does it go from here? Kate Freeman said once, it was one of those rare ideas where we understood it and then there wasn't anything left to do. I think that's completely right. We know it's not perfect. It turns out that linear oxygen exposure time model assumes that it was only exposed to oxygen once and that was it. So it can't account for lateral transport. It can't account for oscillating redox conditions. And Rick and some co-authors worked on that a little bit, and it turns out when you calculate a lateral estimate of exposure time, certainly in nearshore environments, it actually tightens up the relationship even more. I think for me, what I want to do next is to start thinking about how do we estimate this oxygen exposure time in the deep past. Because understanding how our Earth evolved to be an oxic planet has got to be tied to the carbon preservation side. But we need a proxy for that exposure time that's going to survive, right, in the rock record. So it's likely to be something that's related to metals or metal isotopes. So my last piece of miscellaneous advice, don't be afraid to take on a hard problem or a problem that requires a lot of work to get the information. And you never know where something's going to go in 24 or 25 years. So thank you very much. Ultimately, a paper is significant because the community uses it. And it's a tremendous honor to know that our paper has had this level of support and impact for so many years. Thank you also to my nominators. It's really important that all of us nominate papers that we think are important, that mean something to our work, people that deserve to be recognized for their work. And we only have, awards are only as excellent as the suite of nominations that they get. I want to thank all of my champions and mentors, my funding agents, my lab group, and all of you for being here today to help us celebrate. Thanks.